Okay guys, so in this video what I'm going to do is work through about 25 questions that are randomly selected from across the quarter to help you try and get ready for the final. So in this first question here, we're given 3 different descriptions of scientists that are engaging in activities that are part of the scientific method, and we're asked to come up with the missing words. So there are sort of about 4 terms that we need to be aware of here. The first is observation. The second is experiment. The third is hypothesis, and in particular we should say scientific hypothesis, but we're just going to say hypothesis. And then the fourth is theory. Occasionally you'll hear a 5th term, or a 5th term will be appropriate, which is law. So you should kind of know how to recognize these different things. So it says that James sets up a something or other in which he will carefully stir the water in an insulated container, keeping track of the force required to stir the water and then measure any temperature rise in the water. He hopes to find out whether the energy of stirring can be transformed into heat. So this is not a hypothesis, because a hypothesis attempts to explain the result of several experiments. It isn't a law, because a law is something that summarizes the key results from many experiments, but it doesn't explain why you get those results. It isn't a theory, because a theory is a well-tested hypothesis. And it's not an observation, because an observation is a single measurement. So really the only one that makes any sense is that it is an experiment, because an experiment is a well-designed procedure to gather data about a system. So yeah, it's got to be an experiment. All right, so this one is an experiment. Okay, the next one, it says Jean-Baptiste, after studying the way heat flows through solid materials, discovers a something that says the rate of heat flow is proportional to the difference in temperature per centimeter, and he measures the constant of proportionality of several substances. So this is far too elaborate to be an observation. This is not an experiment, because after studying the way that heat flows through solid materials, he's not doing something here. He's like contemplating results of things, and he's doing a calculation. So it is not an experiment. Now it says that the rate of heat flow is proportional to the difference in temperature per centimeter, but it doesn't tell you why. It doesn't say the reason that this is. So it's not a hypothesis or a theory, because those things always tell you why something is happening. What it is it's a law. It's a summary of a large number of experimental results. So it is most definitely a law. It doesn't tell you why, it just tells you what happens. Okay, Sadi proposes that something, Sadi proposes that substances become hot when rubbed, because the pressure of the rubbing squeezes out a fiery, bright substance he calls caloric. So, this is interesting. It's got this because, right, which means that you're trying to explain something. So this puts it into the kind of idea of being probably either a hypothesis or a theory. It's kind of trying to explain why things happen. He's saying that when you rub them, you squeeze out the heat, which is interesting. Right, Sadi proposes the something that substances become hot. So this is not an observation, because it's a proposal based on, it's just an idea, isn't it, right? It isn't an experiment, because he's not doing something, he's thinking about something. It isn't a law because it's not summarizing the results of a large number of experiments. It's proposing why something happens. Now, is it well tested? If it's well tested, it would be a theory. If it was tentative, it would be a hypothesis. This is tentative. This is just one guy coming up with an idea, so this has got to be a hypothesis. All right, so and that's generally how we're going to analyze these questions. Now, if you don't know, it's got to be one of these 5 things. So, better to put something rather than to leave it blank. Okay, it says here are 4 sketches of substances. Okay, each sketch is drawn as if a sample of the substance were under a microscope so powerful that individual atoms could be seen. Okay. Decide whether each sketch shows a sample of an element, a compound, or a mixture. So if it's an element, we have only one atom type present. And the different atom types in this case are indicated by the size of the sphere and the color. So there is only one of them that meets the criteria of being an element. So we've done the elements. So then the next thing is that it's a compound. And the thing about a compound is you've got one substance, but 2 or more atom types. Okay. So if I look in the first case, there's only one type of molecule. It's the one that has a gold atom and a red atom bound together. So this is definitely a compound. This guy has got 2 types of molecules. So it is not a compound. And the final one only has the one type of molecule where they've got the 2 of the red ones and 1 of the gold. So it is also a compound. Now a mixture has more than one substance present. More than one substance present. So we've only got one left to categorize, substance Z, and we're hoping it's going to be a mixture, and it is. There's 2 substances present here, 2 different types of diatomic elements. So that guy is a mixture. Okay, so in this next problem, you're given some information about hydrogen chloride. So hydrogen chloride is a diatomic molecule. It's going to be a hydrogen atom connected to a chlorine atom, and it has a melting point of minus 114.8 degrees Celsius. So temperatures below that it will be solid, and temperatures above that it will be a liquid. And then it has a boiling point of minus 85.1. So temperatures above minus 85.1, hydrogen chloride is a gas. And what you're asked to do is move these sliders in the windows A, B, and C until it represents the state of hydrogen chloride at the different temperatures indicated. So what you need to do is first of all make sure that the diagram is illustrating hydrogen chloride molecules, which is going to be 2 different atoms bound to one another. And then you need to decide if you have a solid, liquid, or a gas. So at minus 113, you are lower than the melting point, so you have a solid. At minus 96 degrees Celsius, you are in between the melting point and the boiling point, so you're going to have a liquid. And at minus 73 degrees Celsius, you're above the boiling point, so you're going to have a gas. So in a solid, the particles are orderly arranged and are very close to one another. In a liquid, the particles are organized they're not very organized at all. They're sort of like arranged in a disordered manner, but they are close to one another. And in a gas, the particles are a long way apart from each other and they are moving around in rapid random motion. So the images that I have selected indicate how this is representing the solid, liquid, and gaseous state of hydrogen chloride. So that's the deal there. Okay, question number 4. So this question is all about the conservation and conversion of energy. So energy is subject to the first law of thermodynamics that says that energy cannot be created or destroyed. So the amount of energy that you start with is always exactly the same as the amount of energy that you end with. But what can happen is energy can be converted between various forms. And in this case, we're going to be converting energy between potential energy and kinetic energy. So to begin with, our bicyclist is stopped at position A. So it has 0 kinetic energy, but it can go downwards, so it has some, in fact all of its energy is potential energy. And then as it rolls downhill, it will it will turn its potential energy into kinetic energy. So it'll increase, I don't know where it's going to get to, at B, and it might have lost, it looks like it's lost about, well, here's the lowest point. We got 1, 2, 3, 4, 5, 6 there. 1, 2, 3, 4. So 4 out of 6, it's lost 2/3 of its potential energy. So it would have 33% of that left, and 67% of it is over there, right? So that's what's going to happen, right? So basically, as it rolls down the hill, it loses potential energy and picks up kinetic energy. And then as it rolls back uphill, you guessed it, it slows down and it turns its kinetic energy back into potential energy. So where does it have the highest, where would it have the highest potential energy? Well, when it's the highest above the floor of the valley. So that would be F. Okay. Where would the cyclist have the lowest potential energy? Well, that's when it has the lowest distance above the ground. So that would be D. Now, D is also where it's going to have the highest kinetic energy because it's turned all of that potential energy into kinetic energy. So the third answer there is D. And where would it have the highest speed? Well, kinetic energy is associated with movement, so it's going to have the highest speed where it has the highest kinetic energy. And then it says, would the cyclist's kinetic energy be higher at A or C? Well, at A, we're told that it's stopped. So at C, it is most definitely going to be going faster, and it's going to have more kinetic energy because it will actually be moving. Would the bicyclist's potential energy be higher at A or C? Well, it's higher above the valley floor at A than it is at C, so that means that it would have higher potential energy at A. Would the cyclist's total energy be higher at A or C? Well, it actually would be the same. Because remember, energy isn't created or destroyed, it's just transferred between the different forms. And finally, it says, suppose the cyclist or the bicyclist lets off the brakes and coasts down into the valley without pedaling. Even if there is no friction or air resistance to slow her down, what is the furthest point the cyclist can get to? Well, without pedaling, the cyclist can't get further than E because, the energy has to be the same as what it was at the starting point. So it couldn't go up to F without pedaling because that would mean that it would have more energy than what it began with. So it's going to stop at E unless the person pedals to make it up to F, and it'll stop at E. And in this system with no wind resistance or friction, they would just roll backwards and forwards between A and E forever, which would be kind of cool. Alright, so that's the general idea there, and most of these guys are doing okay on that kind of thing. Okay, it says there are 4 sketches below. The first sketch shows a sample of substance X. The 3 sketches underneath it show 3 different changes to the sample. You must decide whether each of these changes is possible. If a change is possible, you must decide whether it is a physical or a chemical change. So, for it to be possible, there has to be no change in the number of atoms of each type. So we're going to want to define how many atoms of each type there are. So to begin with, we've got 4 molecules, and each of the molecules has, by the looking at this, 6 whites. So that's going to be 24 whites, and they also have, each of the 4 have 6 of the grey ones. So that is 24 whites and 24 greys. So these things are only going to be possible if they maintain that number of each atom type. So let's have a look and see if we can see any of them as being impossible. So in this one here, number 1, we see now that we have 1, 2, 3, 4, 5 molecules, and each of them has 6 whites, and each of them has 6 greys. So that would be 30 whites and 30 greys. So that one is impossible. Okay. Let's go on to change number 2. So in this case, all of the molecules that we come up with are of the same type, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them. So 12 molecules, and each molecule contains 2 whites, so that would give me 24 whites, and each molecule contains 2 greys, so that would give me 24 greys. So that one is possible. Okay. So let's go on to change number 3. So in this case, it gets a little more complicated because we've got 2 different types of molecules. So we got 2 molecules that contain 1, 2, 3, 4, 5, 6, 7, 8 whites. So that would give me 16 whites. And then I've got another 2 molecules that contain 4 whites. So that would give me 8 whites, and that gives me 24 whites in total. So that's looking good for this being possible. Then in here, I've got 2 molecules that contain, we have to add these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of the grey ones. And then 2 molecules that contain 2 of the grey ones. So putting all that together, that would be 20 grey, 4 grey, 24 grey. So that one is also possible. So we eliminated one of them as being impossible. So now we just have to decide, are they chemical or physical processes? So the key thing is that a chemical change involves a rearrangement of how the atoms are bonded to one another. And you can see that in both cases that's happened. We've reorganized how the atoms have connected to each other, so these are both chemical changes. So it takes a little bit of caution to add up the number of atoms of each type correctly. So you just take your time and work through it. All right, here we go. This one says, decide whether each pair of elements in the table below will form an ionic compound. Okay, if they will, write the empirical formula of the compound formed. Okay, so ionic compounds, so these are a pair of elements. Ionic compounds are formed between metals and non-metals. So we're going to need to identify whether we have that criteria. So in the first case, we've got iodine, which is a non-metal, and oxygen, which is also a non-metal, so no, it doesn't form an ionic compound. In the second case, we've got strontium, which is a metal, and fluorine, which is in a non-metal, so yes, it does form an ionic compound. So we've got strontium with fluorine. Okay, we'll figure out the formula in a moment. In the third case, we've got bromine, which is a non-metal, with rubidium, which is a metal. So yes, it will form a ionic compound. And we've got one last one to check. We've got sodium, which is a metal, with sulfur, which is a non-metal. So yes, that guy will form an ionic compound. So now we just kind of need to break out our periodic table. So I'm just going to go and grab a periodic table. Maybe. Being a bit slow. So I'm just going to go to my favorite place to get a periodic table from. And we're going to start looking up some stuff. So here's the periodic table. All right. What do we got here? So strontium, there it is in group 2A, so it's a 2+. And fluorine over in 7A, so it's a 1-. So these guys are not going to come together in a 1-to-1 ratio, right? It's going to be 2 fluorines for every 1 strontium. So this will be SRF2. Now we've got rubidium, there it is in group 1A, so that's a +1. With bromine, which is in group 7A, so that's a -1. Now these guys have equal and opposite charges, so they just come together 1-to-1. So that's just going to be RbBr. Now our final pair was sodium with sulfur. So sodium's at the top of group 1A, so it forms a +1, and sulfur is over in group 6A, so it forms a 2-. So they don't have equal and opposite charges, so we're going to use crossover. So that means we need 2 sodiums for 1 sulfur. So it's going to be Na2S. So there we go. The first thing we did was to identify whether we had a metal and a non-metal. And then if we did, we looked up the charges of those elements in the periodic table. And to write the formulas, we did one of 2 things. If they had equal and opposite charges, like rubidium bromide, we combined the ions 1-to-1. If the charges were not equal and opposite, then we used the crossover rule to get the ratio of the ions. So that's it, really. And just remember, if it's in group 1A, it forms a +1. Group 2A, it forms a +2. Group 3A, it's a +3. And then for the non-metal, 7A -1, 6A -2, 5A -3, and that's it. All right, so pretty straightforward. And with the transition elements, it gets a bit more complicated, except for we always know the charges on silver, cadmium, and zinc are +1 and +2 and +2. All right. In the periodic table below, shade the F block elements. Well, that are those guys, and you know what one it is because it is 14 elements across, and there are 14 electrons that go in an F shell. So that's your Fs in here. That's the P block. These first 2 rows in here. That's your S block, and you guessed it, in the middle there is the D block. 2 across, 6 across, 10 across, 14 across. So very easy to remember what's what. It's going pretty well, isn't it? Reorder the list in the table below, if necessary, so that the atoms and ions, so you might not have to do it, are listed in order of decreasing size. Okay, so the first thing to remember is that the size of atoms increases. So they increase like that. The second thing to recognize is this. Anions are made by adding electrons to atoms. So they are always bigger than their parent atom. They're always bigger than the atom that they are made of. And cations are made by removing electrons. So they are always smaller than the atom that they're made from. So in this case, we've got bromine, iodine, and iodide. So bromine and iodine are both in group 7A, but iodine comes after bromine. So what that means is that bromine is smaller than iodine. Now we're going to list these in order of decreasing size, so I should have really written them around the other way to stop that getting confused, right? So iodine is bigger than bromine. Now, what's bigger, iodine atom or an iodide ion? And well, what we know is that anions are always bigger than their parent atom. So iodide is bigger than iodine because we had to add an electron to it. So in order of decreasing size, it's going to go I minus, and then I, and then Br. And that makes sense because every time we go down a row in the periodic table, what are we doing? We're adding another layer of electrons. So they should get bigger, all right? Okay. Okay, here we go. Oh, this looks like ionic compounds again, doesn't it? Oh, we have to identify if it's going to be an ionic or a molecular compound. So ionic compounds, we got metals, plus a non-metal. Yeah? And then molecular compounds, what do we have? We've got non-metals coming together. Now, if we're asked to determine the formula for a non-metal, how we might do it is by looking at the Lewis symbols of the atoms involved. So, for example, if I look at the compound that might be formed between oxygen and hydrogen, I know that oxygen is looking to make 2 bonds and hydrogen is looking to make 1 bond. So a sensible way of reacting these things to achieve that would be to have oxygen react in a 2-to-1 ratio with hydrogen to form H2O. Now, when it comes time to thinking about the formulas for ionic compounds, what we'll do is we'll think about the charges of the ions involved, and we'll either combine them in a 1-to-1 ratio if the sizes of the charges are the same, or we'll use crossover rule to get the formula. So that's what's going to happen here. Okay, so we probably need a periodic table, don't we? Just so we can figure stuff out. All right, there's a periodic table. So let's see what we've got here. Metal with a metal. So it is neither an ionic compound or a molecular compound. Neither. Okay. Calcium with sulfur. Metal with a non-metal. So that means that it is ionic. Helium with krypton. Now a little bit sneaky here. Noble gas with a noble gas. Noble gases don't react, right? So neither. Okay, it's not going to form a compound. Little bit tricky, that one. You want to be on the lookout. That's for the A+ students, right? Okay. So we've only got one where we're trying to figure out the formula, and it's an ionic compound. So calcium with sulfur. So let's go over to our periodic table. Calcium is in group 2A, so it forms a 2+. And then sulfur, there it is, over in group 6A, so it forms a 2-. So these guys have equal and opposite sized charges, So they're going to come together in a 1-to-1 ratio. So it's going to be CaS. All right, so a little tricky there because metals don't combine to form compounds with other metals. That's going to be neither. And then noble gases don't form compounds, so that's going to be neither. So a little, you know, you can't expect all of them to be without a little trick or two. All right, let's have a look at this one. It looks like a unit conversion problem. Let's read what it says carefully though. A student sets up the following equation to convert a measurement. The question mark stands for a number the student is going to calculate. Fill in the missing part of the equation. So what's missing is what's in this blue box here, right? So they're going to do a unit conversion, aren't they? All right. So how do we do unit conversions? By multiplying by a conversion factor. And what are conversion factors? Conversion factors are fractions. So the first thing to realize is that they're going to be multiplying by a fraction. What's missing is a fraction. And this fraction is going to have meters on the top and centimeters on the bottom. And now we need to put, because we're going to get rid of meters and leave behind centimeters. So now we need to put in our numbers. Remember, the 1 always goes beside the unit that has a prefix, and the power of 10 goes beside the unit that doesn't have a prefix. And in this case, we know that there are 10 to the minus 2, or that centi is equivalent to 10 to the minus 2. So that just goes like that. And then you can see boom, boom, and that would be it. Now, you don't have to calculate anything here. All you have to do is fill in what goes in the box, which would be that, okay? Now, you don't need the parentheses if you don't want them, all right? So it would be valid without the parentheses. Okay, this looks like it's the same thing. It is, but the tricky thing here is, can you see that we're doing a conversion on something that is cubed? And that means we must remember to cube our conversion factor. So what I'm going to have to do here is convert centimeters cubed to meters cubed. So I'm going to be multiplying by a fraction that has meters on the top, centimeters on the bottom, and then I got to cube it. And I know 1 centimeter is the same as 10 to the minus 2 meters. So that's what I'm going to be multiplying by. So this term here is what goes in the blue box there. Okay, and yes, you should be writing these out neatly like I have been here. Okay, so this problem is one of the more challenging ones. It says that cobalt-2 chloride forms several hydrates with the formula cobalt Cl2.xH2O, where x is an integer. So that just means that x is a number like 1, 2, 3, etc. It says if the hydrate is heated, the water can be driven off, leaving pure CoCl2 behind. So what's going to happen is this. You're going to have like 1 mole, 1 unit of this hydrate. You're going to heat it up, and that's going to leave you with 1 unit of the cobalt chloride, and then X moles or X units of the water will leave as a gas. And what it says is that suppose a sample of a certain hydrate is heated until all of the water is removed, it's found that the mass of the sample decreased by 45%. What hydrate is it? Which is really just code for saying what's the value of X. So what I know is that if I had 100 grams of this, 45 grams of it would leave as water, and 55 grams of it would remain as cobalt-2 chloride. What I also know is that I get X moles of water for every 1 mole of cobalt chloride. So if I take the ratio of the number of moles of water to the number of moles of cobalt chloride, I'm going to get what X is, right? So it's about a mole ratio problem here. So what I've got to do is turn each of my grams here into moles, and then divide my moles of water by my moles of cobalt-2 chloride. And then that'll tell me how many moles of water I get for every 1 mole of cobalt chloride. So I need to go and calculate my molar masses. So I'm going to need periodic table. So I'll grab that guy. And there we go. We're going to need to find the molar mass for cobalt and the molar mass for chlorine, and then of course hydrogen and oxygen. So 55 grams of cobalt chloride and 1 mole of cobalt-2 chloride. Let's see what we've got. We've got 58.93 plus 2 times 35.45. If you don't like doing this, there is the potential to use an online molar mass calculator. You can just Google and find one of those. And so this ends up being 129.83. So 129.83 grams of cobalt chloride in every 1 mole. So I do that math, and I see that I would get 0.42363 mole of cobalt chloride. We'll write that out in a more sensible manner in a moment. Now, for water, we got 45 grams of the water, and I know that in 1 mole of water, there are 18.02 grams of water. And how I get that is by adding together the mass of 2 hydrogen atoms and 1 oxygen atom. So what does that give me? 45 times 1 on 18.02. And so that ends up being that I've got 2.4972 mole of water. Okay, so cobalt chloride, for every 100 grams, it contains 0.424 moles of CoCl2 and 2.497 moles of water. So what have I got to do now to get my X? I want to do my moles of water for every 1 mole of cobalt chloride. So I just got to do 2.4972 divide 0.42363, and that's going to give me that X in the formula there. Right, divide 0.42363, and it ended up being 5.9. Okay, 5.9. So it must be, well, X has to be an integer, so the closest integer to 5.9 is 6. So that's it, right? So it is cobalt chloride dot 6 H2O. Okay, because it says X has to be an integer. So the fact that we got 5.9 is okay, because we have to round it to the nearest whole number. All right, what do we got here? Ammonium perchlorate, and it gives the formula, which is nice, is a powerful solid rocket fuel in the space shuttle boosters. It decomposes into nitrogen gas and chlorine gas. Oh, nitrogen gas, chlorine gas, and oxygen gas, and water vapor, releasing a great deal of energy. Now, decomposition just means that we have just the one reactant falling apart, and it makes nitrogen, N2, chlorine, oxygen, and water. So we're going to have to do definitely a good job on balancing this. So let's just get to it. Nitrogen, I've got 1 on the left, but I've got 2 on the right. So I'm going to need 2 of those guys. Now they balance. Hydrogens, 2 times 4, that gives me 8 on the left. And I've only got 2 on the right. So I'm going to need 4 of those. And then chlorines, 2 times 1, so I've got 2 on the left, and I've got 2 on the right, so they're good. and then oxygens, 2 times 4, that's 8 on the left, and then I've only got 2 at the moment, so I'm going to need 4 of those. So how does it all look? Whoa, 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 whoa. Error, error, error. When I was doing oxygens on the right, I forgot to take into account the 4 over here. So 4 oxygens over here plus another 2, I've got 6. But if I bring that up to 4, then 2 times 2 is 4 plus another 4, that would give me 8. So there we go. So 2 ammonium perchlorates decomposes to give 1 N2, 1 Cl2, 2 O2s, and 4 waters. Okay, that's good. So that looks like it's all balanced. I'm happy with that. Always double check that you got your balancing correct before you do any stoichiometry calculation. And yes, you should write out the balanced equation before you ever think of getting going, or you are likely to make an awful mess of this. It says calculate the moles of water produced by the reaction of 0.1 moles of ammonium chloride. So 0.1 mole of that guy. So that's got 2 sig figs, and we want to know how many moles of that. Okay, so 0.10 mole of NH4Cl4, and to do a moles to mole conversion we use the mole ratio. We get 4 mole of water for every 2 mole of ammonium perchlorate. So moles of ammonium perchlorate cancel out, and so what does this mean? It means that we get 0.20 mole of water, and I know I got it right because my moles of water is what's left over in my units there. 2 sig figs, and the answer will be 0.20, and MOL is the abbreviation for mole. Okay. This looks like an interesting problem. It says compound A reacts with compound B, so A plus B, to form only one product, C. Okay, so whenever they're saying this is that whatever the mass of A is that reacts, plus whatever mass of B reacts, then the mass of C is just going to be equal to the mass of A that reacted plus the mass of B that reacts. According to the law of conservation of mass, that's what's got to happen. Alright? So that's what it's all about. So it says compound A reacts with compound B to form only one product, compound C. It is known the usual percent yield of C in this reaction is 61%. So the maximum possible amount would be just the sum of however much of each thing reacts, right? That would be the theoretical yield. So it says, suppose 2.5 grams of A are reacted with an excess of compound B. So what that means is you have more B than what can possibly react. Just like if you were burning a candle, you have more oxygen in the atmosphere than could possibly react, right? But in total, you get 2.5 grams of C. So 4.3 grams of C. So I know how much of B reacts, right? So if 2.5 grams of that reacts, and I get 4.3 grams of C, right, at the end of it. And that represents 61% of the possible amount that I could get. So the theoretical yield, 100 on 61. Right, the theoretical yield is going to be a bit bigger than that. All right, so 4.3 times 100 on 61. The theoretical yield that I could get would be 7.05 grams. Right, that's my theoretical yield because I only get 61% of it. So that's what it's asking here. What was the theoretical yield of C? Round your answer to the nearest 0.1. So it was 7.049. So it should just be 7.0. All right, 7.0. I should extend this out a little so you can see what I'm talking about. 49. So how did I know that? I knew that this is my actual yield. It represented only, well, let's do it properly. 4.3 grams equals the actual yield. Percent yield equals my actual yield over my theoretical yield times 100. So I want to get my theoretical yield, so that's going to be my actual yield times 100 over my percent yield, and that will give me, ooh, hang on a moment. Let's do it this way. Divide both sides by 100, so my percent yield divide 100, right, would be my actual yield over my theoretical yield, and my percent yield in this case was 61%. So 61 on 100 equals my actual yield over my theoretical yield. So then that's just 0.61 obviously. Then actual yield on 0.61 will equal my theoretical yield. Alright, so my actual yield that I got was 4.3 grams. I'm going to divide that by 0.61 and that'll give me my theoretical yield. So there's a variety of ways of kind of like doing this, but I kind of hurried it, I guess. So same way, ended up with my theoretical yield equals 7.049 grams. Grams in there. Alright, oh that was actually percent. Alright, so that's where we're at, 7.049. So, yeah, that's it. 7.0 would be my theoretical yield. So if 7.0 is my theoretical yield, then the mass of B that reacts, right, with my 2.5 grams of A, it's gotta be, what is it gotta be? It's gotta be 4.5 grams, right? Is that right? 4.5 it is, because 2.5 plus 4.5 would give me 7.0. So how much was reacted? How much of the B must have reacted? Well, if theoretically I can make 7 grams, and I know that 2.5 reacts of the A, then 4.5 must react of the B to get that up to the 7. So that's a little bit confusing because they gave you the actual yield, which is only 61% of the real yield. All right. Okay. Woohoo! All right. Feel like, you know, that was a little clunky, but maybe watch it back once or twice, and you'll understand what I'm getting at. Okay. This is another one, so I got a chance to redeem myself. Each week, Cape Chem, a manufacturer of fine chemical, uses up 1,000 kilograms of compound A and 950 kilograms of compound B in a reaction with only one product, compound C. So A reacts with B to give C. And we're going to react these in a ratio of 1,000 kilograms to every 950 kilograms, right? And so you would say, and that if this is all working perfectly, you would make out of that 1,950 kilograms of compound C. So what is the maximum theoretical mass of compound C that Cape Chem could ship each week? Well, it has to be 1,950. Now they want it to the nearest kilogram, so we do want to put that dot on the end to indicate that trailing zero there is actually significant. And then now it says, suppose on average the percent yield of C in Cape Chem's chemical reactors is 72%. So this is your theoretical yield, and then your percent yield is 72% of that. All right. So what that means is that the actual amount that you're going to get is 72% of this number. So 72% as a fraction is just 0.72 times 1950 kilograms. So 72% of that number is 1,404 kilograms. So what are you going to get? How much are you actually going to get if you're achieving 72% yield? That much, 1,404 kilograms, 72% of 1,950. So, about 540 or so kilograms just kind of goes missing, right? Okay, it just gets lost along the way. Not so great, huh? Okay. So this is all about analyzing a Lewis structure, and they nicely give you the Lewis structure, and then you have to count the number of bonding pairs and the number of lone pairs around the nitrogen atom. So make sure you kind of focus in on what you're meant to be focusing in on. So there's the hydrogen, there's the carbon, and now these are bonding pairs that are near the nitrogen. So hopefully what you can see is that there are 3 bonding pairs. They make up that triple bond, and then there is just the one non-bonding pair, or what we call a lone pair. Alright. So how many have we got? 3 bonding pairs, 1 lone pair gives a total of 8 electrons around the nitrogen. So always pay attention to what they're asking for. They wanted pairs. So don't say 6 and 2. Alright. Okay, let's have a go. Oh, we've seen something like this before. It says reorder the list in the table below if necessary so that the atoms and ions are listed in order of decreasing size. So let's pop our periodic table up, and we know that these guys, that atoms get bigger as we go that way, right? The atoms get bigger as we go that way. The other thing that we know is that cations are smaller than the atoms that they're made from, what we call their parents, right? Their parent atom. So that's going to be important here, because what that's going to telling us is that sodium is bigger than sodium plus, because we make a sodium plus by removing an electron from a sodium. Now the question is, what is bigger? Is it rubidium or is it sodium? All right. And remember, they get bigger as we go down, so rubidium is bigger than sodium. So in order of increasing size, it's got to go rubidium is bigger than sodium, which is bigger than sodium plus. So it is Rb Na Na plus. So similar to the other question, but we had a cation instead of an anion as the ion that was present. Alright, here's one with an anion. Alright, remember that anions are bigger than their parent atoms, because we make anions by adding electrons to the atom. So anions are bigger than their parents, bigger than the atom that they're made from. So that's telling me that bromide is bigger than bromine. So now we've got krypton, right? So here's bromine and here's krypton. And so what's bigger? Well, atoms get bigger as we head to the left, and as we go down a group. So krypton is smaller than bromine. That is, bromine is bigger than krypton. So the order is going to go bromide, bromine, krypton. Bromide, bromine, krypton. Okay, not too bad. Moving right along. Question number 20. Name each of the acids listed in the table below. Well, there are 2 types of acids. There are binary acids, where you have hydrogen combined with one other thing, and they are all described as being hydro something ic acids. And the thing that's missing there is the stem name of the anion that is formed by X here. So what's going to happen is we're going to have HAX. A is just some multiple of hydrogen atoms. That's going to make A lots of hydrogen atoms, and then it's going to make an anion with a charge of A minus. So this first one here is of that sort. It's a binary acid. So it is HI, and it's going to dissociate to give one hydrogen, and then iodine, because there's only one hydrogen, is going to have a single minus charge. And if you don't know, this is the iodide anion, and the stem name is IOD. So this is called hydroiodic acid. Now, so that's how you name a binary acid. Now, if you look at all of the other acids, they contain a polyatomic anion. These are what are called oxo or oxy acids. Oxo or oxy acids. So for oxy acids, we have a similar scenario. Your acid is going to dissociate to give some number of hydrogen ions, and then an anion, which in this case is going to be a polyatomic anion with a charge that balances out the number of hydrogens that I have. So in the first one here, what's going to happen is this. H2CO3 is going to give me 2H pluses and CO3 2 minus. You see that? Because a 2 and a 2. In the second one, HClO3 gives me 1H plus, and then the ClO3 has a single minus. And then in the fourth case there, we've got HNO2. So I get 1H plus, and then that tells me that the NO2 is a single minus. So the reason for doing this is I need to know, in order to name an oxyacid, what the anion's name is. And this is why, because what's going to happen is anions that are 8s, they come from ic acids. Alright, so if I have a nitrate, that's going to be nitric acid. And then ites, they come from us acids. So what I have to do is I have to go through and name each of these anions. I'm going to look the names up in a table of polyatomic anions. So that is the carbon 8 anion. This is the chlorate anion, but this one is the nitrite anion. So what it means when I'm naming these acids is 8s become ics. So the first one there is going to be carbonic acid. The second one is going to be chloric acid. But the third one, because it's an ite, is going to be nitrous acid. So there are my three names for my oxyacids. So it's a little bit more complicated for the oxyacids versus the binary acids. All right. So in this problem here, I have to deduce the formula of an ionic compound, and then I have to give the name of the ionic compound. So the formula is pretty easy. If my ions have equal and opposite charge, they combine 1 to 1, and if they don't, then they're going to combine according to the crossover rule. So a quick scan here indicates that none of them are going to be combining 1 to 1. They all have different size charges between the anion and the cation. So I've got to do crossover for all of them. 2 oxygens means I get 2 minus on the oxygen means I get 2 ions. 3 plus on the ion means I get 3 oxygens. SN2 plus, N3 minus. I need 2 nitrogens and 3 tins. So SN3, N2. Mn2 plus and P3 minus. You can see it's going to be the same ratio because the charges are the same, Mn3 P2. And then finally copper single plus and S2 minus. I need 2 coppers and 1 sulfide, so Cu2S. So getting the formulas is pretty easy. So now I need to name them, and to name them I have to give the name of the cation followed by the name of the anion. Now the difficulty is for the cation, these are all monatomics. I have to decide whether it needs Roman numerals, and if the element is in group 1A, 2A, 3A, or is silver, cadmium, or zinc, it doesn't need Roman numerals to indicate the charge. If it is outside of that selection, then I'm going to have to put the charge in Roman numerals. So this is going to be iron 3. This is going to be tin 2. This is going to be manganese 2, and this is going to be copper 1. Now if you Google these names, they have common names, and you may or may not be getting the common name or the systematic name. Now to name an anion, it's pretty easy. You take the stem name of the parent non-metal atom, and then you add the ending IDE. So no indication of the charge. So that's going to be oxide, nitride, phosphide, and finally sulfide. And there we go. So it's not inconsiderable. Okay, here we go. Now it says fill in the systematic names of the following chemical compounds. Note, for compounds containing hydrogen, you can give the common name instead. So I scan the list and see, are there any hydrogen containing ones? And there is NH3, and NH3 has the common name ammonia. Now, when I look at the rest, I can see that they are all compounds formed between non-metals, which means that they are all covalent compounds. And how I give the name of a covalent compound is I give the name of the first element unaltered. Then I add the name of the second element, but I just take the stem and add the letters IDE to the end. So just like naming an anion. And then finally what I got to do is I've got to give a numerical prefix, a Greek prefix, so that's mono, di, tri, etc., to indicate the number of the element. So the name of the first element is unaltered, but the name of the second element, we just take the stem and change it to the ending to IDE. Then we're going to put prefixes. So this is going to be chlorine for the first one, oxide, and then prefixes, dichlorine, hepta for the 7. All right. For the next one, PCl3. Now, phosphorus, the first element unaltered, and then chloride. I have 3 chlorine, so that's tri. Now, we don't ever put mono when there's only one of the first one, because if you give the element name, it implies that there is at least one. The next one is Cl2O3, so chlorine, and then oxide. There were 3 oxygens and 2 chlorines. And then finally, finally, but we've already done ammonia, I guess. So PCl3, so phosphorus, chloride, and there are 5, PCl5. So that is penta, and again, we don't have the mono when we only have one of the first one. Now, in general, we only use the mono if there's one of the second one. So a good example would be carbon monoxide. All right, balancing. These guys should be all whizzes at this. You had an extra credit assignment on this, so we just have to hop in and get it on. The fact that there's oxygen there automatically makes you feel a little nervous, doesn't it? Because you might have to use that half coefficient to get it to balance in the first pass. So here we go. So let's begin with silicon. We've got 4 on the left, we've got 1 on the right. What about if we put a 4 there? There we go, that works. Then we've got hydrogen, we've got 10 on the left, and at the moment we've got 2 on the right. What about if we put a 5 there? That works. And then now we've got the dreaded oxygen. We've got 2 on the left, and then we've got 4 times 2, that's 8, plus another 5, that's 13. So if I put 13 on 2 there, that'll fix it. All right, the only problem is we're asked for the small set of whole number coefficients. So we've got to multiply everything by 2. So 2, 8, 10, and 13, and there we go. And we can't simplify any further, so we know that we are good. All right, we're getting near the end here. Problem 24. It says, one day in a lab, while taking apart a complicated distillation apparatus, your friend Gina, an expert chemist, says this: ammonium salts heated with aqueous hydroxides form ammonia, water, and a salt. So a salt doesn't mean like, you know, beating somebody up. It means the same thing as saying an ionic compound. Okay, so there's 2 reactants, an ammonium salt and an aqueous hydroxide. So hopefully you can see that this thing here, the first reactant here is your ammonium salt. It is an ionic compound containing the ammonium ion. And then the second thing here is your hydroxide. It is sodium hydroxide. So now we want to look for the products. So the products are going to be ammonia, NH3, water, H2O, and then it says a salt, which would be an ionic compound. So what are we going to have left over? Well, what we've got left over here is pretty clearly we've got sodium ions that we haven't accounted for, and then we've also got these guys, which are sulfate anions that we haven't accounted for. So they're going to combine, because they don't have equal and opposite charges, in a 2-to-1 ratio, Na2SO4. So the big thing here was figuring out what that salt was. So it's Na2SO4. And now that all that's all consistent now, isn't it, with what the description that Gina gave. An ammonium salt reacts with a metal hydroxide to form ammonia, water, and a salt. And the salt in this case is the sodium sulfate. So all we've got to do now is get everything to balance out, right, by adding the correct coefficients. So if I look at nitrogens, I can see that I've got 2 on the left, 2 times 1, but I've only got 1 on the right. So I am going to need 2 of those guys. And if I look at the other thing that leaps out here are sodiums. And if I look on the left, I've got 1, but on the right, I've got 2. So I'm going to need 2 of those guys. So that kind of gives me the really obvious stuff, right, that I need 2 of those. So now we're into the less obvious stuff, which is the sulfurs, the hydrogens, and the oxygens. Now sulfur, got 1 on the left, and I've got 1 on the right. So sulfur is good. And then what about oxygens? Oxygens is going to get complicated. It always gets complicated with oxygen, doesn't it? So I've got 4 there, and then 2 times 1, so that's 6 on the left. And then on the right, I've got 4 there, and 1 there, that's only 5. But if I put a 2 there, then it works. 4 plus 2, that gives me 6. And the reason I chose to change that guy is I didn't want to mess with anything that was going to jack up my sodiums and my sulfates. So now oxygens balance. And then the last thing to check are the hydrogens. So 2 times 4 is 8. And then 2 times 1, that's 10. Then 2 times 3, that's 6. And then plus a 2 times 2, that's 4. So 6 plus 4 is 10. So the hydrogens balance. So it looks like we get 1 ammonium sulfate, 2 sodium hydroxides to give 2 ammonias, 2 waters, and 1 sodium sulfate. All right, that was decent, right? There's a couple of tricky ones in here, and that's fine. So this looks like it's another one. It says, looking up one sunny afternoon from a general chemistry textbook, your friend Raphael says this: soluble metal oxides form hydroxides when dissolved in water. So what's going to happen is that is my metal oxide. And then I'm going to dissolve it in water. And the product will be a hydroxide. So what kind of hydroxide is it going to be? It's going to be cesium hydroxide. All right. Now cesium is in group 1A, so it forms +1 ions, and hydroxide, if you look in the table of polyatomic ions, is -1. These guys have equal and opposite charge, so the formula for cesium hydroxide is just CSOH. But we aren't quite done, because we've got a balance now, right? We've got a balance. So the first thing that leaps out to me here is that my cesiums don't work out, right? Cesium, I've got 2 on the left, and I've only got the 1 on the right. So I'm going to have to multiply that guy by 2. Now let's go on to oxygens. I've got 1, 2 on the left, and I've got 2 on the right. So my oxygens are good. And then hydrogens, I've got 2 on the left, in the water, and 2 times 1, 2 on the right, so my hydrogens are good. So that's it. So cesium oxide plus water gives 2 cesium hydroxides, and they're going to be in the water as well, so we should probably put that as AQ. So everything is nice and balanced. Pretty tricky, because you've got to use all of your knowledge of chemistry to answer those guys. Okay, that concludes me working through 25 practice problems. I hope you find it helpful. Good luck with your final exam.